Okay, good evening. Welcome to Geometry Lecture number 12, or Geometry Project number 12. Today we're going to look at section 2.3 of Geometry Revisited. This section is called coaxial circles. This is a very short section, so this lecture is only going to be 5-10 minutes. We're going to look at one very specific family of circles described by the equation x squared plus y squared minus 2ax plus c equals 0. And let's look at the three possibilities. C is less than 0, C equals 0, and C is greater than 0. Okay, so first let's do C is less than 0. So you'll see that this equation simplifies to be x minus a squared plus y squared minus a squared plus c equals 0. Which is x minus a squared plus y squared equals a squared minus c. Okay, now this is going to be true for all of these things. So now let's look at the equation c is less than 0. Now remember, c is fixed, and a can be well, a varies. Well, if c is less than 0, then negative c is positive, and we have this equation x squared minus a squared plus y squared equals r squared. The minimum value of r is going to be minus c, and a can range over anything. So we're going to have a circle centered at a, whose radius is a squared minus c. Now remember, c is negative, so the radius is slightly larger than a squared. So we might have a circle centered at 0, 0, whose radius is the square root of minus c. Say it's something like that. We might have a circle centered over here. The radius is going to be slightly larger than a. Well, in this case we're at minus a. So that circle will extend just past the the y-axis. And in fact, the farther out we get, the closer and closer this radius is going to actually get to a. So that's sort of neat. Alright, that's the case. Sorry, I don't have a lot of room. Let me do something here. Let me just write this equation up here. X minus a squared plus y squared plus a squared minus c. Okay. So we looked at the case c is less than 0, in which case a can be anything. What if c equals 0? Then we just get x minus a squared plus y squared equals a squared. Well, that's easy. All the circles, no matter where they are just tangent. Sorry, that's supposed to be the center. No matter where they're centered, are just tangent to the y-axis, even if they're centered over here. So we get a family of circles like that. And the last case, c is greater than 0. Now, that means if a is 0, this thing's negative. So that's going to be a problem. So in this case, if c is greater than 0, we have to have a greater than square root of c, or a less than negative square root of c. And so now you get the picture that they drew in the book, which is a nice little family of circles. Looks like that. And this is called a pencil of circles. So that's really the only thing they discuss is this family of circles. And let's take a look now at the one theorem they show in the book. So let me do a little bit of erasing, and I'll be right back. Okay, so here's the one theorem that they show in this chapter. Theorem: if the centers of three circles form a triangle, there is just one point whose powers with respect to all three circles is the same. So this is really just a proof by picture. So we're going to look at three circles whose centers form a triangle. you'll remember from the last section that the locus of points whose powers are the same with respect to any two circles is a line perpendicular to the line segment connecting the centers of the circles. So for these two circles, the locus of points whose powers are the same might be here. For these two circles, the locus of points whose powers are the same is going to be perpendicular to here, so it might be here. And lo and behold, the point of intersection here, because it's on this line, has the power that's the same with respect to this circle and this circle. The point of intersection, because it's on this line, has the power that's the same with respect to this circle and this circle. But since that means this point has the same power with this circle, and this circle, this circle, so this means this one point, and that one point only, has the power that's the same with respect to all three circles. So I have to tell you I'm a little confused by this section. So in the first half of the section, which is only the first half of one page, it defines what a pencil of circles is, and that pencil of circles is given by the equation x squared plus y squared minus 2ax plus c equals 0, c fixed, a varies. That's called a pencil of circles. Then they prove a theorem about if three triangles, three circles have centers that form a triangle, there's just one point whose powers are the same. There must be some connection, there must be some reason why they put these two things together, although I have to say I don't quite know what it is. It's kind of two interesting facts. But that's really it. The common point, I forgot to mention, the common point of intersection here is called the radical center of the circles. And maybe we're going to come to something later on that talks about this. There's a very interesting problem associated with this section, problem number 1, which I'd encourage you to take a look at. Very clever little geometry problem. Tomorrow we're going to get back to triangles in section 2.4. But today was just sort of a light, easy lecture. If you have the book, the problem number 1 is a very clever little problem. It took me about 20 minutes last night to figure out how to do it. Anyway, hope you enjoyed this lecture. Tomorrow we're going to move on back to triangles a little bit. Alright, thanks for watching.